Hello everyone, welcome to the class of Discrete Mathematical Structures. Today I'll be teaching a topic in Module 5 under trees. The topic name is about simple definitions, basic properties and examples. Myself, Dr. Madhura, working as an assistant professor in the Department of Mathematics, Sai Vidya Institute of Technology, Bengaluru. First, we will know the definition for a tree. A graph G is said to be a tree if it is connected and has no cycles. So the graph should be a connected graph, means there should be a path between every pair of vertices, and it should not form any cycles. Forming cycles means it should not be a closed curve such that the beginning and the end point will be the same. So a graph which has no cycles and which is connected is called a tree. A graph which is a tree is usually denoted by the letter T. Say for example, with two vertices we can see one edge formed here. Figure 1, 2, 3 shows all our trees. So with these three vertices in figure 2, we have formed another tree. So there should not be an edge between these two vertices. And similarly here also, we observe that the path is connected. There is an edge between every pair of vertices and it is connected. Means if we start from a vertex here, I'll be able to move to the all the vertices of the entire graph. So it gives us the connected graph. And cycles means it does not form a closed curve. So we observe figure 4 and 5 are not trees. Figure 5 is a disconnected graph. We have different components here. So there exists more than one component. That is the reason figure 5 is not a tree. And figure 4 is not a tree because it forms a triangle here. So it's a closed curve. So this does contain a cycle and hence figure 4 is not a tree. The graphs 4, 5 shown above are not trees. As I mentioned, that is fourth graph contains a cycle and the figure 5 contains, it is not connected. Let us know the definition for a tree now. A pendant vertex of a tree is called a leaf. Means a vertex with degree 1 is called a leaf. Forest, group of trees forms a forest. Each component of a disconnected graph is a tree and such graphs form a forest. We observe the figure 5, there are different components here. So each of these components of a disconnected graph, this is a disconnected graph, this forms a tree together and these are together individually they are trees and group of trees together forms a forest. Let us now consider this important theorem. A tree with n vertices has n minus 1 edges. So any tree with n vertices has always n minus 1 edges. The alternate form of the statement. For a tree with n vertices and m edges, we have the resultant always m equal to n minus 1. M is the size of the tree and n is the order of the tree. N stands for the number of vertices in the tree and m is the number of edges considered in the tree. So any tree with n vertices and m edges has always this expression to be true, m equal to n minus 1. So let us alternately can be written as cardinality of E equal to cardinality of V minus 1. Now let's see the proof. Proof is by induction on n. So we consider the mathematical induction on n and prove the resultant. So in mathematical induction, there are two steps. One is the basic step and followed by the induction step. So in the basic step, we observe that n equal to 1, suppose we assume n equal to 1, then m will be equal to 0. n minus 1. So 1 minus 1 will be 0. It is a true statement because when I consider one vertex, there are no edges in it. So this becomes the isolated vertex. There cannot be considered any edges. It does not form a loop. If it forms a loop means it is not a tree. It is just a graph. So with n equal to 2, number of edges is m equal to 1. When we substitute into the formula, this becomes 2 minus 1, so m equal to 1, which is again true. So as we observe here, a graph wherein I have taken two vertices because n should be 2. And between these two vertices, we can draw only one edge to form a tree. If we try to draw more than one edges, it forms a cycle, hence it will not be a tree. Now with n equal to 3, the number of edges m will be equal to 2. And again with the help of a graph, it is observed. So we observed that for all these basic values, the theorem is satisfied. So basic step is satisfied or basic step is true. Now moving ahead to the induction step, we assume that the result is true for all trees with n vertices, where n is less than or equal to k. According to mathematical induction, in induction step, we always assume that the resultant is true for all n less than or equal to k. And assuming this, we prove the resultant for n equal to k plus 1. So consider a tree T with k plus 1 vertices. Now in tree T, suppose we assume E is an edge with end vertices u and v as considered in the example here. So I have considered a tree. This is a tree with n vertices with say suppose k plus 1 vertices, and I'm assuming then edge E here whose end vertices are u and v. Now what happens if we delete the edge E? So deletion of the edge E will give us a disconnected graph, will give us disconnected tree, and T minus E has exactly two components, say T1 and T2. So suppose we delete this edge E, then this forms into two components or it becomes like two trees for us. Each of them are trees for us. So it is T1 and T2. So since T has no cycles, both T1 and T2 also will not have any cycles, and hence T1 and T2s are also trees. We had assumed a tree T with k plus 1 vertices, and one of the edge we named it as E, and removal of this edge or deletion of this edge will fetch into two components T1 and T2. Since both do not have cycles, it forms a tree. T1 and T2 are trees. Now both T1 and T2 have less than k plus 1 vertices each. Tree T had k plus 1 vertices. So obviously each one of them components, that is the trees T1 and T2, have less than k plus 1 vertices each. So that we can say it both T1 and T2 satisfies the theorem according to the assumption made. Because in the induction step, we assume that the result is true for all n vertices where n is less than or equal to k. So theorem holds good for both T1 and T2 trees. That is, both T1 and T2 has one edge less than the number of vertices in it. That's what the theorem says, no? So we have n vertices means both T1 and T2 have now one edge less than the number of vertices in it. So total number of vertices in T1 and T2 taken together. So when we consider T1 and T2 being taken together, it is nothing but same as saying T minus E graph. So T minus E, that is total number of vertices in T1 and T2 taken together, which is nothing but in T minus E, is k plus 1. And total number of edges in T1 and T2 taken together will be k plus 1 minus 2. There will be one edge less in both the trees, T1 and T2. So one edge less in T1, so minus 1. One edge less in T2, so minus 1. Together it forms minus 2. So that is why we will be able to write down in T minus E there are k plus 1 vertices, and together there are k plus 1 minus 2 edges, which is k minus 1 for us. So T minus E has k minus 1 edges. So this implies the tree T has exactly k edges. E stands for one of the edge, so which is compensated with this 1 here. So the tree T has exactly k edges. Hence, a tree T with k plus 1 vertices has k edges. We started taking the result with k plus 1 vertices, and now we see that we have arrived at exactly having k edges for it. So that is why we conclude a tree T with k plus 1 vertices has k edges. So thus by induction, we will be able to prove that a tree with n vertices has n minus 1 edges, which is one and the same as saying m equal to n minus 1. So that was the theorem proof for us. Now we will move ahead to the simple problems on trees. Firstly, prove that a tree with 2 or more vertices contains at least 2 leaves, that is pendant vertices. So we have a tree T with 2 or more vertices in it, and we need to prove the result in that it contains at least 2 leaves. Having 2 leaves means it is having pendant vertices. At least 2 pendant vertices are there. Pendant vertices or leaves means having degree equal to 1. So let us see the solution for this. Consider a tree T with n vertices where n is greater than or equal to 2. So we need to take tree with having n vertices, and since in the question it is mentioned that 2 or more vertices are there in the tree, we assume n is greater than or equal to 2. Then it has n minus 1 edges. According to the theorem just now what we proved, a tree T with n vertices has n minus 1 edges. So that is the reason we are writing this tree has n minus 1 edges. Suppose D1, D2, D3, etc. up to Dn denotes the degrees of the vertices of the tree T. Then by handshaking property, sum of the degrees of the vertices is equal to twice the number of edges. So we assume the degree of every vertex as D1, D2, D3, etc. up to Dn because there are n vertices. We have taken up to Dn. And we apply the handshaking property which says summation degree of V, that is sum of the degrees of all the vertices is equal to twice the number of edges, 2 into cardinality of E. So we sum up the left hand side, we add up all the vertices, all the degrees here. So D1 plus D2 plus D3 etc. up to Dn, we are adding all the degrees, which is twice the number of edges in the tree. So number of edges in the tree is n minus 1. So 2 times of n minus 1. Now this is same as saying 2n minus 2 in the right hand side. 2n minus 2. So d1 plus d2 plus d3 etc. up to dn is equal to multiplying the right hand side 2n minus 2. Let us assume this as equation 1. If each of these degrees d1, d2, d3 etc. up to dn is greater than or equal to 2, means we are assuming suppose the degree of every vertex is greater than or equal to 2, then sum of each of these degrees will be greater than or equal to 2 into n because there are n vertices. So the sum will happen to be equal to greater than or equal to 2 into n. But from equation 1, sum of all the degrees is equal to 2n minus 2. So left hand side we can write it down as 2n minus 2 is greater than or equal to 2n. And this gives us a contradiction because 2n minus 2 is never greater than or equal to 2n. So this gives a contradiction for us. So there is at least one d which is less than 2. See, we are assuming each of these as degrees, d1, d2, d3, etc. are all degrees of all the vertices, which is greater than or equal to 2 we have assumed. Because we have to prove that there are at least two leaves, two leaves in the or two pendant vertices in the tree we have to prove. Means degree equal to 1. There are two vertices whose degree is equal to 1 has to be proved. So if degree of every vertex is greater than or equal to 2 only, means there is no degree, there's no graph with degree equal to 1 or degree equal to 0. Means we are taking degree of every vertex is suppose greater than or equal to 2 only, then this becomes a contradiction for us. So there exists at least one degree, one of the D's whose degree is less than 2. So when we say degree is less than 2, degree has to be 1 only. It cannot be 0. Degree of any vertex cannot be 0 because T is a connected tree. We have assumed a connected tree because according to definition of a tree, it should be connected. So if degree is equal to 0 of any particular vertex, then it becomes a disconnected graph. So since d1 cannot be equal to 0, degree of any one of the vertex can be equal to 1. We had just now shown that there should exist at least one of the degrees, one of the vertex having degree less than 2. So we assume one of the degree of the vertex, say d1, degree of one of the vertex, say d1 is equal to 1. Then we have this substituting in equation 1. So d1 is 1. So 1 plus d2 plus d3 is equal to etc. up to dn is equal to 2n minus 2. This is by handshaking property. Whatever the expression we had written in equation 1, we substitute there and we get d1 equal to 1. Simplifying this, sum of d2 to dn is equal to 2n minus 3. We'll denote this by equation 2. Now we again assume in the same manner that every degree d2 to dn, degree of every vertex d2, d3, etc. up to dn is again greater than or equal to 2 we assume. Means remaining vertices degree, we are assuming that degree of every other vertex except d1 is again greater than or equal to 2. Then what happens? Sum of all these d2, d3, etc. up to dn will be greater than or equal to 2 times of n minus 1. We have only n minus 1 vertices here. 2, 3, 4, etc. up to n gives us n minus 1 vertices. So sum when we take up, it will be greater than or equal to 2 times of n minus 1. So this is greater than or equal to 2n minus 2. But from equation 2, we are substituting the left hand side 2n minus 3. d2 to dn sum is 2n minus 3 from equation 2. We substitute that into the left hand side. So we have obtained 2n minus 3 is greater than or equal to 2n minus 2, which is again a contradiction. 2n minus 3 is never greater than or equal to 2n minus 2. So this becomes a contradiction for us. So since we have arrived at a contradiction, the meaning is there exists at least one more d, that is one more vertex degree is equal to 1. So this proves us the result that already we had one of the vertex degree equal to 1. Now again getting a contradiction, we have one more degree equal to 1. So this proves us the resultant that we have at least two vertices whose degree is equal to 2. That is having leaves. So we can observe these by simple examples what I have considered here. Suppose I consider only two vertices. These two becomes the leaves itself, having degree equal to 1. Suppose we assume three vertices and form a tree. We observe B and C are the leaves here, having degree equal to 1. And in the third graph, third tree, here again we have 4 leaves existing. So a tree, any tree, whichever is being considered, it always arises that there are at least two pendant vertices. So thus in T there exists at least two vertices of degree 1. So two vertices of degree 1 is same as saying leaves or pendant vertices. Hence the proof for us. We'll see another problem. Suppose T1 equal to V1 E1 and T2 equal to V2 E2, V2 trees. Means we have considered T1 and T2 as two trees whose vertex set are V1 and V2 and edge set are E1 and E2. If number of edges in E1 is equal to 15, means number of edges in the first tree is equal to 15, and number of vertices in the second tree is equal to 3 times of number of vertices in the first tree, determine V1, V2, E2. So let's see how to do the solution. Consider V1 equal to E1 plus 1. So number of vertices is equal to number of edges plus 1, or same as saying m equal to n minus 1, or same as reading n equal to m plus 1. So we already familiar or given value for E1 we will substitute, which is 15 plus 1 gives us 16. So V1 value will be equal to 16, or number of vertices in the first tree is equal to 16. Now it is given that V2 is equal to 3 times of V1. Since we know the value of V1, we substitute it. So 3 into 16 gives us 48. So number of vertices in the vertex set, number of vertices. Next, we find out, or we have to find out number of edges in the second tree. So we have the expression V2 equal to E2 plus 1. So number of vertices is equal to number of edges plus 1. Considering the same, we substitute or we obtain the value of E2. E2 is V2 minus 1, m equal to n minus 1. A tree with n vertices as always n minus 1 edges. So which is 48 minus 1, which is 47 for us. So this is how, given from the data, we will be able to find out cardinality of V1, V2 and E2. Third problem. Suppose that a tree T has n1 vertices of degree 1, n2 vertices of degree 2, n3 vertices of degree 3, etc. up to nk vertices of degree k. Then prove that n1 equal to 2 plus n3 plus 2 n4 etc. up to k minus 2 into nk. So in order to prove the resultant, we consider the handshaking property here and apply the resultant. So let's see how to do. Total number of vertices. There are n1 vertices, n2 vertices, n3 vertices, etc. up to nk vertices. So if we add up all these, we will get the total number of vertices in the tree. So which is n1 plus n2 plus n3, etc. up to nk. Now, total number of edges in the tree will be total number of vertices minus 1. So n1 plus n2 plus n3 etc. up to nk, the whole thing minus 1 gives us the total number of edges in the tree. So given that T has n1 vertices of degree 1, n2 vertices of degree 2, n3 vertices of degree 3 etc. up to nk vertices of degree k. Means there are totally n1 number of vertices having degree 1, n2 number of vertices are having degree 2. In the same manner, nk number of vertices are having degree k is the given data for us. So we apply handshaking property. Sum of the degrees of all the vertices is always twice the number of edges. We take the sum now, left hand side. So there are n1 vertices of degree 1. So that's why we have n1 into 1. We have n2 vertices of degree 2. So we have written n2 into 2. n3 vertices of degree 3. etc. up to nk vertices of degree k. So nk into k equal to twice the number of edges. So total number of edges in the tree is n1 plus n2 plus n3 etc. up to nk minus 1. So we have taken the same thing in the RHS multiplied by 2 because it is twice the total number of edges. We need to simplify this to get the required resultant. So n1 plus 2 into n2 plus 3 into n3 etc. up to k into nk is equal to 2n1 plus 2n2 plus 2n3. Each number is multiplied by 2 here. So minus 2 is the last term. Now let us group the like terms. So we have n1 and the right hand side it is 2n1. So taking n1 to the right hand, we obtain n1 to the right hand. 2n2 gets cancelled on both sides. Simplifying for n3, it is n3 in the left hand side. Similarly, 2n4, etc. K minus 2 into nk. I take the constant minus 2 to the left hand, we'll get plus 2. So this is same as rewriting the expression for n1 in the required format. That is n1 is 2 plus n3 plus 2 n4 etc. up to k minus 2 into nk. So just by using the handshaking property, we were able to get the required resultant. And before that, we need to analyze that if there are n vertices in the tree, there are n minus 1 in the n minus 1 edges in the tree. So theorem concept is applicable as well as the handshaking property. Next we have fourth question. If a tree has 4 vertices of degree 3, 2 vertices of degree 4 and 1 vertex of degree 5, then find the number of pendant vertices in tree T. Pendant vertices means having degree equal to 1. So again, application of the handshaking property. So there are 4 vertices of degree 3, 2 vertices of degree 4 and 1 vertex of degree 5. So obviously there will be some number of pendant vertices in the tree T. So let us assume there are capital N number of pendant vertices in the tree T whose degree is equal to 1. So total number of vertices in the tree will be the N also should be considered here because it gives the pendant vertices for us having degree equal to 1 plus. From the data we have 4 vertices of degree 3 being given. So 4. Then there are 2 vertices of degree 4. So we have to write down 2 vertices. That's why 2 is written. And there's 1 vertex of degree 5. So that's the reason 1 here. So total number of vertices gives us the sum of all these, which is n plus 7. And remember, n is here. Total number of pendant vertices that is having what degree equal to 1. So total number of edges will be total number of vertices minus 1. So n plus 7 minus 1 gives us n plus 6. And it is given from the data that 4 vertices of degree 3, 2 vertices of degree 4 and 1 vertex of degree 5 is existing in the tree. And obviously there are n number of vertices whose degree is equal to 1. So we apply handshaking property for this. That is, sum of the degrees of all the vertices is equal to twice the number of edges. So we have n into 1 because there are n vertices of degree 1. So n into 1. There are 4 vertices of degree 3. So 4 into 3. There are 2 vertices of degree 4. So 2 into 4. And finally there's 1 vertex of degree 5. So 1 into 5 is twice the number of edges. So number of edges is n plus 6. So 2 into n plus 6. Let us simplify this and obtain the value of n. So left hand side on simplification will be n plus 25. Right hand side simplifying we obtain 2n plus 12. So this gives us the result for n equal to 13. And we have denoted n as the number of pendant vertices in tree T. and that is the required answer for us to find the number of pendant vertices or the leaves in the tree. So here we obtained n equal to 13, means there are 13 pendant vertices in the given tree. So some practice questions are given for the purpose of more understanding. Can just practice these questions and have a better clarity about the topic. Thank you for watching.